Our universe is vast and mysterious. The answer to its origin, according to the prevailing scientific theory, is the Big Bang. Imagine a time when there was no time, and space itself was confined to an infinitesimally small point. This point, unimaginably hot and dense, contained the seeds of everything we see around us today. Then, in a cataclysmic explosion of energy and matter, the universe as we know it was born. The Big Bang theory is a scientific model supported by decades of rigorous observation and experimentation. The Big Bang wasn't just a single event, it was the beginning of a process that continues to this day. In its first fleeting fractions of a second, the universe underwent a period of rapid expansion and cooling known as inflation. During inflation, the universe expanded faster than the speed of light, stretching out the fabric of space-time. As the universe expanded and cooled, energy began to condense into matter, following Einstein's famous equation, E plus mc2. This process led to the formation of the first fundamental particles, quarks, leptons, and bosons. These particles eventually combined to form atoms, stars, and galaxies. As the universe continued to cool, these fundamental particles began to combine, forming protons and neutrons. These protons and neutrons combined to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. After about 380,000 years, the universe had cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. The Big Bang theory is backed by solid observational evidence. One of the most compelling pieces of evidence is the redshift of distant galaxies. This phenomenon, known as the Doppler effect, also applies to light. The light from distant galaxies is stretched out, shifting towards the red end of the electromagnetic spectrum, indicating that these galaxies are moving away from us. Another crucial piece of evidence is the cosmic microwave background radiation, CMB, a snapshot of the universe when it was just 380,000 years old. The abundance of light elements, such as hydrogen and helium, also supports the Big Bang theory. These pillars of proof, redshift, CMB, and light element abundance, form the bedrock of our understanding of the universe's origins. Imagine a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins embedded within it move farther apart. This analogy helps visualize the expansion of the universe. The raisins represent galaxies, and the dough represents the fabric of space-time. The expansion of the universe doesn't mean that galaxies are flying through space. Instead, it's the fabric of space-time itself that's stretching, carrying the galaxies along for the ride. This expansion is a fundamental property of the universe, a consequence of the Big Bang. The universe's expansion means it was once much smaller and denser than it is today. Light is the language of the universe, carrying information across vast cosmic distances. By studying the light from distant objects, astronomers can piece together the history of the universe. One way astronomers study the universe is through spectroscopy. Imagine passing sunlight through a prism, splitting it into its component colors, creating a rainbow. Similarly, astronomers use instruments called spectrographs to split the light from stars and galaxies into its individual wavelengths. This spectrum of light reveals the chemical composition, temperature, and motion of the object being observed. Another powerful tool in the astronomer's arsenal is the telescope. By combining observations from different telescopes and using sophisticated computer models, astronomers can create detailed maps of the universe. The cosmic microwave background radiation, or CMB, is a faint afterglow of the Big Bang. This radiation permeates all of space and can be detected with sensitive radio telescopes. The CMB is incredibly uniform, with a nearly identical temperature in all directions. However, it also contains tiny temperature fluctuations, just a few parts in 100,000. These fluctuations represent the seeds of the large-scale structures we observe in the universe today. By studying these fluctuations, astronomers can learn about the conditions in the early universe. The discovery of the CMB in 1964 was a landmark achievement in cosmology. Spacecraft like COBE, WMAP, and Planck have been launched to study the CMB in exquisite detail. The Big Bang provided the ingredients for the universe, but it was the force of gravity that brought these ingredients together to form stars and galaxies. Gravity caused denser regions of the early universe to collapse under their own weight, forming the seeds of galaxies. Within these proto-galaxies, clouds of hydrogen and helium gas began to collapse further, eventually igniting as stars. These first stars, massive and short-lived, flooded the universe with intense radiation, forging heavier elements in their cores. As these stars reached the end of their lives, they exploded as supernovae, scattering their newly created elements into space. These elements became the building blocks for new generations of stars and planets. The cycle of star birth, life and death continues to this day, shaping the universe we live in. The Milky Way, our own galaxy, is thought to have formed through the merger of many smaller galaxies over billions of years. The early universe, while remarkably uniform on large scales, contained tiny density fluctuations. These fluctuations, amplified by gravity over billions of years, gave rise to the vast cosmic web of galaxies and galaxy clusters we observe today. Galaxies are not randomly scattered throughout space. Instead, they are organized into vast clusters and superclusters, separated by immense cosmic voids. Dark matter, an invisible form of matter that doesn't interact with light, plays a crucial role in the formation of these large-scale structures. Although we can't see dark matter directly, its gravitational influence can be inferred from its effects on visible matter, like galaxies. It acts as a cosmic scaffolding, providing the gravitational pull for galaxies to cluster and form the cosmic web. By mapping the distribution of galaxies and galaxy clusters, astronomers can test cosmological models and refine our understanding of the universe's origins and evolution. The Big Bang Theory may seem like a distant and abstract concept, but its implications are all around us. The very elements that make up our bodies, the carbon in our DNA, the oxygen we breathe, were forged in the cores of stars that lived and died billions of years ago. We are literally made of star stuff. The technology we rely on every day, from smartphones to satellites, is a direct result of our understanding of the laws of physics. The Big Bang Theory provides the framework for understanding these laws, enabling us to develop new technologies and push the boundaries of human knowledge. The Big Bang Theory is a testament to the power of human curiosity and our relentless pursuit to understand the cosmos and our place within it. From a single, searingly hot, incredibly dense point, our universe was born, expanding, cooling, and evolving over eons into the cosmos we observe today. The evidence supporting the Big Bang Theory is overwhelming, from the redshift of distant galaxies to the cosmic microwave background radiation, to the abundance of light elements. The Big Bang Theory not only explains the universe's beginnings, but also provides a framework for understanding the evolution of stars, galaxies, and the very fabric of space-time. The Big Bang Theory's impact extends far beyond the realm of science. It's a story that continues to unfold, inspiring future generations to explore the unknown and unravel the mysteries of the cosmos.